Routing and scheduling. Routing and scheduling are amongst the most fundamental problems we have in networking today. And so today in this talk, what I would like to do is actually to present you how programmable data planes and P4 can help us innovate and improve on these kind of like old problems, but still, of course, very interesting. So before I dive into the problems and the solutions, let me first introduce what I mean by routing, what I mean by scheduling. So routing is the process of computing and maintaining the set of paths alongside which we forward traffic in our network. That's routing. Scheduling is the process of controlling the packets that are flowing alongside these paths. So as I said, these two processes are fundamental in our networks today. But I would still argue that they are limited in different ways and across different dimensions. So for routing, I think the problem is that routing is actually very flexible, right? It's implemented most of the time in control plane, in software, so you can pretty much change the way it works very easily. The problem is actually it's quite slow. And so we'll see how we can speed things up using programmable data planes. That's for routing. Scheduling, on the other hand, is extremely fast. So scheduling is happening, of course, in the data plane on a per packet basis. And if you look, for instance, at P4 enabled hardware, it's happening at nanosecond level. So it's hard to beat this. But it's also extremely unflexible. It's actually one of the largest part of the programmable data planes, which is not programmable today. And of course, after my talk, I hope to convince you this is actually possible also to program. So before I give you the solutions to this problem, let me actually motivate them a little bit more and hopefully convince you that indeed routing and scheduling are still interesting to look at, of course, in our field. So first, let's look at routing and the problem of computing and maintaining paths in our network. So if we look at the high level, what routing is, essentially, I would say it's four main tasks. So if you put yourself in the shoes of an IP router, you are essentially doing four things all the time. The first thing you are doing is that you are detecting any failures or any change in the network topology, like a new link appearing, a new old link disappearing, one of your neighbor failing, etc. So you detect changes to the network topology. Once you have detected the change, the next thing you do is that you flood this notification in order to let everyone know, at least in the context of a distributed routing protocol, that there is a change in the network. In the context of SDN or centralized routing, what you will do is tell the controller that there is a change in the topology. The third task is actually recomputing the path. So there is a change in your network topology, you need to adapt your routing paths, you need to adapt also your forwarding state, which brings me to the fourth and last step, which is to actually update the forwarding state after the change. So these four tasks are really fundamental and kind of like define routing as we know it today. And actually all of them, except for the notification part, all of them are pretty slow, at least in the worst case. So if you look at all of these four tasks, you can see that they can all take more than a minute to perform in the worst case. So for instance, it can take more than a minute to detect that there is a failure happening in your network, at least when we are speaking about internet failure, so remote failures that are like outside of your network premises. Let me give you actually a little bit more details about this one with this graph over here. So here, what I will show you is a CDF, so a cumulative density function, of the time in between a failure that happens in the data plane. So we'll call that T0. T0 is the moment there is a failure happening. And then T1 will be the time the control plane knows about it. So T1 minus T0 is essentially the downtime in which the control plane didn't know that something was wrong actually in your network, the detection time, if you wish. And here are the results. So these are actually measurements we did in the wild across hundreds of routers, and details are in the papers that I will refer to at the end of the presentation. But what is important here to see is that in the worst case, you can see it can take up to 10 minutes actually for a router to even figure out that there is a problem in the internet. And also what is interesting, I think, is the median point, so the 50% mark, where you can see that actually it can take more than 100 seconds for routers in the median case, BGP routers, to actually figure out that there is a remote failures. So this is crazy to me. So during almost 2 minutes, routers are happily pushing traffic into a black hole without actually blinking. So that's not good. Detection time, the fact that this is more than a minute, clearly you will agree, I hope, that this is not something we want in our network. The second problem is computation. So if you put yourself in the shoes of a, let's say, a router in a highly, let's say, demanded environment, like for instance in an internet exchange points. So if you look there in the time it takes to recompute the forwarding state, the routing state, sorry, upon a large event, it can take more than a minute, 1.5 minutes, to recompute the routing state. That's not good. That's not good enough for networks today. And it's not only about computing, but it's also about updating the forwarding states once you have recomputed. And here again, it takes a lot of time. So even though updating a single forwarding entry in the data plane takes only a few microseconds, so it's pretty fast. But when you multiply a small number of microseconds times almost 1 million of entries to update, it leads to a big number. So all these three essentially are too slow, I would argue, at least in the worst case again, for today's demand, today's network demand. So that's not good. We need to do something better, and again, I think we can do something better with programmable data planes. So the second problem I would like to talk about in this presentation is the problem of scheduling, which I'm arguing is fast, that's good, but again, fixed, and so too essentially inflexible. So how do we improve this, and what's the problem? Well, the problem is that if you are network operators and you are working in different environments, perhaps you're working for an ISP, a data center, a wide area network, an IXP, well, you will have different requirements, and you will henceforth also have different scheduling objectives. And so each of these scheduling objectives will actually lead to slightly different scheduling algorithms. And here I'm listing a few examples of, like, for instance, you may want to minimize tail latency, you may want to minimize flow completion time, or enforce maximum fairness. There are like dozens more scheduling algorithms and objectives, really only listing a small subset of them. So depending on what kind of like network you are running and where you are, you will actually have different objectives. Perhaps you will even have more than one objective at the same time. So that's kind of like a wide variety and a wide diversity of scheduling algorithms. At the same time, though, it has been shown pretty recently in 2016, this is a great paper I advise you to take a look at NSDI 16, that a universal packet scheduling algorithm does not exist. So what does it mean is that there is no one algorithm to rule them all. So you cannot just hope that one algorithm will help you solving all the objectives at the same time. So you need somehow multiple algorithms to kind of like live at the same time, at least in your devices, if you want to optimize for multiple objectives. And this is where the clash happens. So if you have a need for diversity and a lack of generality, so that's actually a pretty big push for flexibility. There is a great, let's say, saying here is that you cannot have everything you want, but you can have anything you want. At least if you have flexibility, you can kind of like reprogram your network to do objective A, reprogram it to do objective B, etc. So you can have anything, even though you cannot have all of them at the same time running all the time. That's why I think flexible scheduling is actually important in our networks today. And here, if we think about it though, so if you take like, let's say a brand new, even like state-of-the-art, let's say Tofino switch out of the box, so P4 enabled hardware, pretty much everything is programmable. You have like the ingress pipeline is programmable, the egress pipeline is programmable. Of course you have limitations, but you can still change the behavior there. But still, what is in the middle, the traffic manager, so essentially where the scheduling and the queuing logic is actually being implemented, that part is not programmable. So we end up here with an almost fully programmable pipeline with like a pretty big piece in the middle which we cannot touch. So we can reconfigure it, but we cannot program it. And that's, I would argue, not good enough. And so what I will show you also in the presentation later on is how we can actually make these Tofino devices as well programmable in the traffic manager, at least try to approximate that behavior somehow. So this will be the kind of like planning for the rest of the talk. First, I will talk about fast routing, how do we speed things up there by offloading routing tasks. Some of these routing tasks are mentioned to the data plane. Then I will mention, or I will speak about how we can make scheduling more flexible by, in a sense, modifying at runtime how packets are mapped to queues. And this you can actually do in P4 enabled hardware. You can do this in P4. So we'll see how we can kind of like devise this mapping policy in a smart way, hopefully. And then the last part of the talk briefly, because I will probably run out of time, I would like to mention a few thoughts about what I see interesting, I see are interesting problem in the routing / forwarding world moving forward as well. So with this out of the way, let us start with faster routing. So as I told you, we have these 4 main tasks, and so we are in the P4 workshop. So what about we try to kind of like offload them to a P4 enabled hardware? So what about we try to detect, notify, compute, and update all in P4, all in the data plane? So how do we do that? And can we actually do it? Was it even a good idea? So let me first here speak about detection. And I would like to kind of like point at that even though it might take a router hundreds of seconds, BGP router, hundreds of seconds to figure out that something is wrong on an internet path, if you think about it, the traffic which is flowing over that internet path is immediately impacted by the failure. So you have like a routing process that takes 100 seconds to figure out that something is wrong, but the data plane immediately could see it. So that's the intuition here. If we could somehow enable the data plane to analyze the traffic signals in real time, it could then inform the control plane that actually something is wrong alongside the path, and then tell the control plane to converge on another path, for instance, faster. So that's really the key intuition here. So tracking traffic. So think of traffic as a signal that you are like kind of monitoring in real time and tracking in real time in the data plane, and then take action based on this. So what kind of signal am I talking about? Well, if you think about internet traffic, of course, a lot of it is still UDP today. I know that QUIC is rising and UDP is rising, but still a lot of the traffic we are looking at today is TCP-based. So in TCP-based communication, what you have is when there is a failure, the TCP endpoints will see that there is a failure because the packets are being dropped somewhere, and so they will start retransmitting the packets over and over again. So if we look first at one single connection, so we have a source and we have a destination. So let us say that at some point the source sends a packet with sequence number 500, perhaps the packet has a size of 500. That packet goes through without any issue. There is an ACK that follows that acknowledges the next expected sequence number of 1000, let's say, and then boom, there is a failure. Of course, the source doesn't know that there is a failure. It's just now that whatever packets the source will send will be dropped on the floor because of that failure somewhere in between the source and the destination. So at some point, the source will try to transmit a packet again. Let's name that point T. So at time T, the source sends the next packet with the next expected byte of 1000. That packet, because of the failure, is dropped. So what happens? Well, when the packet is dropped, of course, you detect that through a timer. And by default, the minimum timer, at least on Linux, tends to be 200 milliseconds. So after 200 milliseconds, you will see the first retransmission that will appear. Then there will be an exponential backoff. So in TCP, whenever you retransmit, so you transmit the first time after 200 milliseconds, then the next time will be after 400 milliseconds. So you kind of like double the retransmission time in between consecutive retransmission. So the second retransmission will happen at 600 milliseconds after the original transmission. And then the final one will happen 800 milliseconds after that, because there will be yet another exponential backoff. So we're talking about 1.4 seconds after that. So that's what is happening if we look really at one single connection, of course, in ideal situation. There is no other noise, no nothing. It's just like the impact of that very specific clean failure on that single connection. So now multiply this by, let's say, 100,000 flows that are kind of like experiencing the failure at the same time as these flows. So what you will observe and what you will see is actually a wave of retransmission. So all these flows that are experiencing the failure roughly at the same time, they will also start to retransmit roughly at the same time. So these flows are not synchronized. It's not that my flows and your flows are sending exactly at the same time. So there will be some variance. So what you can expect to see if we were to actually plot this, so what I will show you is kind of like a plot of the number of retransmission as a function of time. And if we assume, for instance, that the failure happens after 1 second and that I have 100,000 flows, what you will see is a sequence of waves of retransmission. So there will be a first wave, then there will be a second wave, a third, a fourth, a fifth, etc., etc. And so one thing interesting here to see is that you can see that the waves are like shrinking in amplitude. And the reason why is actually because of this exponential backoff. So all these TCP sources, they will be retransmitting, but as the backoff increases every time, they will become less and less synchronized, if you want. And so this is why these kind of like waves will actually spread over a longer period of time. That will actually decrease the amplitude. So you can think of this as the area of each of these waves as being equivalent, because we have 100,000 flows that are retransmitting. They will all retransmit sooner or later, but the area will actually grow. So, the area will not grow, but the curve will actually spread out. And in order for the area to be maintained constant, you need to decrease the amplitude accordingly. So what it means is that actually the signal is fading away, as you can see. After a few retransmissions, the signal will be almost gone. So what we want, essentially, or what we were trying to do in this project, is to actually capture this signal in the data plane. So essentially create, if you want, a P4 program that would monitor the traffic in real time, monitor this retransmission in real time, and then kind of like scream whenever there is a failure so that the control plane can immediately, or as fast as possible, let's say, move away from it. And of course, this is challenging. Why? Well, because in practice, the internet is not a nice place, and there are always packet loss that are just due to noise. I mean, the internet, after all, provides a best effort service, so there is no guarantee packets will make it, even though there is no failure. So we need to take into account this as well. So clearly, the curve will not be as nice as the ones I just showed in the previous slides. As I said, the signal is fading away. So if you look here, right, after 4.5 seconds, the amplitude is half of the original amplitude in the first wave. And it will continue to shrink very quickly after that. So we really don't have a lot of time here in order to capture this signal. So that makes it harder, right, because we need to be at the beginning of the signal in order to capture it. So the signal is fading away. And also, I'm talking about aggregating signals across hundreds of thousands of flows. And that means that it's pretty hard, right? Because you need to start like keeping per flow state. And if you don't know that, you will, I'm sure, like learn this in the future. It's not a good idea to keep per flow state in a device. So this is usually an actually motivation for rejection as well in your paper. So please take this into account as well. So how do we solve these challenges? Well, we solve these challenges using, let's say, pretty, I would say, intuitive techniques, but it's not that we can look at the entire signal, so because of scalability reasons. So we need to actually select a subset of the signal. And if we select a subset of the signal, well, better actually be select a subset that has a higher signal to noise ratio than the original signal. So essentially, we try to kind of like zoom in on the sub-signal, which is better for our application. And so that's exactly what we did in this work. So in order to kind of like reduce the effect of noise, we only look at some type of retransmission, not all of them. So I'm sure you know, if you have followed like an undergrad lecture on networking, that TCP will retransmit differently if there is a single loss or burst of loss. So in one case you will have a fast retransmit, in the other case you will have a timeout. So we actually track the latter type. We don't track the first type. To actually kind of like try to compensate for the signal fading away very quickly, we actually zoom in on very active flows. And the reason is that these active flows, they will retransmit faster because there is a lot of packets that are being sent on them. And so that will actually enable us to track the signal sooner as well, rather than to keep kind of like tracking the signal later on in the flow. And then classical techniques here, in order to kind of like track a compound signal with a limited amount of resources, we develop like scalable techniques to sample these flows, and also probabilistic data structure to scale this thing up. I won't go into the details here, but I will refer you to the paper at the end of the talk. What I would like to tell you, though, is that it actually works pretty well. So if we think, for instance, first about the question of accuracy, our experiments show that doing this kind of like inference of a failure according to data plane traffic can lead to accuracy above 80% in most of the cases. And you might think, well, 80% is not that great, right? But actually, what happens when we got it wrong, so when we say there is a failure and there isn't, what happens is that we shift the traffic on another path, but which is also working. So essentially, we are creating a traffic shift. It's not like we're dropping traffic whenever we are wrong. And of course, you can tweak the system if you want to make it less sensitive, at the expense, of course, of missing then some failures. So the system is accurate, and the system is also fast. I mean, was my goal at the end, is to actually show you that you can make routing faster and detection faster in this case. And the cool thing here is that in our experiments, we showed that in the majority of the case, the inference time was below 1 second. So remember where we started from, right? 100 seconds, that's the kind of like median detection time in the internet for a BGP router, and we brought that down to less than a second, or like a second. So that's kind of like 2 orders of magnitude saved by kind of like offloading the detection task to the data plane. So I would say it's pretty significant, and so I would also argue it's a good idea to do. So that was for detection, which was kind of like the first task I wanted to talk about. So let me now talk a little bit more briefly about the last 2, which are actually I think the hardest ones, the computation and the update. As I said, notification, there is not much there to do. You want to flood your messages on the entire network, and there are efficient flooding techniques that exist there already. So nothing to be too fancy there. Computation and update, though, this is pretty a little bit more sophisticated. After all, I'm talking about having the data plane computing routing paths, a task which is typically done, of course, in the control plane today. So how do we do that? How do we have switches, P4 switches, let's say, compute the forwarding state and update that without even a controller being there? There will be a controller still, but the controller won't be active in the computation of the forwarding state per se. So this is actually possible to do, and it's not always a good idea, but the fact that it is possible is something that you can then build upon in some of your applications, depending on your use cases. So let me actually show you, or like briefly tell you how you can actually do that in P4. So for this, I will use this simple example here above my head of four routers, A, B, C, D. There is a destination network connected to A. Oops, it's that one. And there is a source here that we look at is the router D. And you can see that the router D has 2 output ports that we label with 0 and 1. So here, what I will describe you is a P4 program and how you can actually structure that P4 program on router or switch D in order for that switch to compute its forwarding state on its own in the data plane. So for this, of course, you will need the P4 program. And one thing which is key is to actually observe that if you want to do this, so have the switch data plane update its forwarding state without a controller populating a table, is that you need to find a way to store the forwarding state in a register. So for those of you who know before in the room, you know that this is actually one of the rare stateful constructs that can be updated by the data plane itself at runtime. So you need to store the forwarding state in registers, and essentially the forwarding state is a classical one. Of course, you have like a port, you have a cust, and you have a path. Well, I'm looking here at path vector-like routing. So we store the forwarding state in registers, and that's one thing. And then I need a little bit of, let's say, controller provision state. So I mentioned the controller is not active in the computation, but I still need to tell my switch something about the topology in order to compute meaningful path. And this the controller has to do beforehand. One of the things is the cost of the weight of the path, for instance. We're talking about computing, let's say, shortest path entry. Well, I need to tell the switch that this link has a cost of 1, that link has a cost of 10. So there will be one table, extra table, that will contain the link cost. And that won't change. You can actually program it in a static fashion. And a last thing I need as well in order to make this happen is to have another table that map a destination network, a prefix, for instance, with the corresponding entry in the register. So I need to tell that, for instance, prefix 10/8 maps to index 50 in my little example. And that also can be done kind of like statically almost at the beginning when you boot the network, and then you let the switch do the job of computing for you after that. So that you can actually write this program. We wrote that program, and that is totally okay in P4. It's not a short program for sure, but it can it does work. So you have this kind of like forwarding state now encoded on switch/router D. Now let's look at how we actually compute here things. And this is pretty much kind of like textbook application of distance vector / path vector routing. We use path vector routing in our example because at least enable us to detect loops a little bit more easily. So what we'll have is that each switch will regularly kind of like send a vector which just contains the best known information it has for reaching every single destination. So for instance, A here will advertise to all its neighbors they can reach the red destination, which is locally adjacent to it, with a cost of 0, with a pass, of course, of just A. And if we assume that the upper pass is, takes a little bit more time in terms of delay than the lower pass to reach D, then D will actually receive the information from A on the lower pass first. And so here, what you need to do when D receives that message, D, of course, needs to update its forwarding state now, which is stored in a register. So you need to do a little bit of computation here. You can do that in P4, and the computation is really simple. So what you are doing is just you take the cost that you know, and then you compare it against the cost which is advertised plus the link cost on which you receive it. And in this case, it's pretty easy. We just booted a network, so the original cost was infinity, and now we learn a cost of 10 to reach the destination right. So it's clearly better, so we'll actually have the switch update its forwarding state. So the cool thing here is that really that message arrives in the packet, it's in the data plane, the switch P4 program reads that message, parses it, runs the logic, and then after that packet is out, the forwarding state has immediately changed now. So there is no controller, it's really happening at line rate, if you wish. So it takes like a few nanoseconds for the state then to be updated. And of course, after sometimes you will have the message that goes over the upper pass that will also reach D, and then D will once again update its forwarding state. So here, I want to stress one thing, and that's an important one because it shows one of the fundamental trade-offs in doing this thing in the data plane versus doing it in the control plane, is that here we only maintain the best pass in the forwarding, in the registers. So the forwarding state only remembers the best pass. That means that if you are D and you learn a new best pass, you forget completely about the other one. So this is very different, of course, when you do this task in the control plane. In the control plane, you maintain a full routing table, and D will just know that it can reach the destination either via A or via C. So here we'll actually throw away the former, and we'll only keep the best pass. And that's, of course, like one of the trade-offs we have to make. So that means that when you lose, for instance, when there is a failure and you lose the best pass, you will actually need to relearn another pass at that time. Of course, you can make sure that since you can detect it very fast, to have A, again, re-advertise the vector at that time. So again, I want to stress this, that this is an important distinction between running things in the data plane versus running things in the control plane. So as I told you, this may look a little bit crazy, and kind of agree with you, but it's doable, so you can implement it. We implemented it in P4.16, so it's around 2,000 lines of code. We're in the process now of porting that also to Tofino. Right now it runs on top of the software model. And our code kind of like can do intra-domain-like routing, so shortest path-based routing, a la RIP, a la SPF if you want, and also policy-based routing a la BGP, so also inter-domain routing. So of course, with trade-offs, right? It's not like it is exactly the same as doing routing in the control plane. So that kind of like shows you that you can also do computation now of the routing state, of the forwarding state, directly in the data plane in P4 as well. Perhaps like to try to inspire you that this is a possibility and that this computation should not only be done in the control plane. That said, I want to give you a disclaimer here, an important one, I think, is that it's not because you can that you should, right? So doing control plane task in the data plane has a cost, and you need to make sure that it makes sense for your specific applications to actually bear that cost. Also, there are some tasks that just you cannot offload to the data plane in the first place. So you think about crypto operations, for instance, in P4 there is not really a lot of, or like not at all even like security operations. So still this is something that you will have to do in software somehow. Also, I wouldn't start offloading, for instance, an exact implementation of the BGP protocol or an exact implementation of the TCP state machine in the data plane. I think probably it will actually not work, and it's actually a bad idea. So you want something which is very restricted, very targeted to what you actually need. And also, as I said, whenever you start offloading things in the data plane, you also need to keep in mind that you are using up hardware resources, and these are scarce. So that means that if you do fancy routing, perhaps you cannot do fancy load balancing anymore. So depending on how much you really need the fast routing, you might actually prefer to do better load balancing, for instance. So again, it's all about trade-offs, but what I'm telling you is that you can actually make routing very fast if you need to. So whether you need to, that's a question that you need to answer. All right, so that was for the first part of the talk about fast routing, faster routing. Let me now speak about faster scheduling, and more flexible scheduling, and how we can actually start to program packet scheduler, even though they are not made to be programmed even in P4 hardware today. So if we want to program our packet scheduler and make this part programmable, we need some kind of abstraction that enables us to kind of like unlock that box and kind of like program, let's say, a scheduling algorithm 1, 2, 3 on top of a common substrate. And here, an interesting substrate that actually was proposed also in 2016 is a PIFO queue. So PIFO queue stands for push in, first out queue. And if you have a PIFO queue, if I give you a PIFO queue implemented in a switch, you can actually implement programmable scheduling. So that means that PIFO queues can make scheduling flexible. So what is a PIFO queue? Well, a PIFO queue is very simple, actually, really. So it's just a queue, as the name indicates. So it's a data structure that can reorder packets arbitrarily at line rate according to their rank. So a PIFO queue assumes that each packet comes with a rank that indicates its priority. And here in my presentation, a lower rank means a higher priority. So a rank of 1 means that it's more important, more prioritized packet than the rank of 2. So PIFO queue can take ranked packets and automatically reorder them so that when you drain the queue from the head, the packets will always live in an order which is in increasing order of rank. So it's kind of like perfect reordering that happens automatically at line rate. At least that's a theory. Let me illustrate this with a simple example. So here we have a PIFO queue that contains 5 packets. 1, 3, 4, so 5 ranked packets with rank 1, 3, 2 packets with rank 4, and then the packets with rank 5. So now, let us say now there is a new packet that arrives with a rank of 2. So the goal of the PIFO queue is always to kind of like respect the ranking of the packets. So this packet with a rank of 2 should be scheduled, should leave the queue in between the packet of rank 1 and the packet of rank 3. So the PIFO queue, if you want, will create a little space, and then we'll put the packet there. So that when the packet are drained from the head of the queue, the packet will be drained perfectly in order. 1, 2, 3, 4, 4, 5. So that's exactly what a PIFO queue enables you to do. So that's nice, this PIFO queue, but how do you actually make a programmable scheduler using these queues? Well, the intuition is actually that you can just kind of like adapt the ranking policy, so the ranking function, which is right there. So you can adapt this according to whatever scheduling algorithms you may think about. You can actually just take a completely blank sequence of incoming packets, run that by simulation, even through normal scheduling algorithms, and get a sequence of ranked packet as an output. That will be the sequence of this scheduling algorithm if run on these packets. Once you have this rank that have been computed by your favorite algorithms, you just give that to the PIFO queue. And then the PIFO queue will automatically enforce this ranking for you. And then, of course, the packets will be drained in order. So it's really all about kind of like figuring out what ranking policy you need in order to minimize flow completion time, ranking policy you need in order, I don't know, to enforce max-min fairness, for instance. And then to rank the packets accordingly, you tag the packets, and then you give that to the PIFO queue, and then it does the job for you. So that, again, PIFO-Q enables us to make scheduling programmable. But there is always a but, right? And the but here is that implementing this in hardware is, of course, challenging. I mean, you would have guessed, right? That nothing is easy. And what is particularly hard here is that, of course, you need a data structure that can reorder these packets arbitrarily at line rate. And so, of course, reordering, when you have only a few nanoseconds to keep this data structure updated, it's, of course, very, very hard. So if you look in the original paper, they introduced this PIFO-Q in 2016. The design, not the implementation, but the hardware design they proposed was able to do that only for a few flows, actually for 1,000 flows, and for throughput of up to 1 gig. That's not that much if you think about, if you want to do that, let's say, on like modern device that can see hundreds of gigabits, of terabits per second of traffic, and many more flows, of course, than 1,000. It also assumed that the ranks in which the packets arrived have a specific property that they are always increasing, which is not always true. So you would like, if you were to implement this in practice perfectly, you would like not to have any assumptions about the ranking of the packets in order for your implementation to actually work. And of course, don't get me started on the time it takes to deploy a new ASIC, right? So deploying new hardware and even designing the new hardware, implementing it, verifying it, and then putting it into the device will take years. So before you have, let's say, a new Tofino 3 switch with a PIFO-Q inside, likely won't happen until years from now, if ever. So that was the question that our quest was that, okay, we cannot really do it today, but can we approximate it? And if we can approximate it, how well can we approximate it? So we like to approximate it at line rate, at scale, and on existing device. And can we do that? The answer is yes, otherwise I wouldn't be here speaking. And we came up with this SP-PIFO approximation of a PIFO-Q. And SP-PIFO actually does run on real hardware. We actually made it run on a Tofino switch. And the idea how we emulate, if you want to approximate the behavior of a PIFO-Q on a Tofino switch that does not support PIFO-Q is by actually leveraging two things. Strict priority queues that are available on Tofino, but also on any, let's say, network device, you have like strict priority queues, typically at least. And the capability we have given by P4, which is to update the mapping between the packets and these strict priority queues at line rate, at runtime. And by doing these two things and packing them together, we actually can approximate the PIFO-Q. So let me give you an example here. So let me first describe an SP-PIFO system, and then I will give you a detailed example of how it works. So as I told you, an SP-PIFO system, we use strict priority queues. So let me just give you an example here with 3 of these queues. So I'm sure you know that system of strict priority queues, what it means is that you have like multiple queues of multiple priority, and you always, when you have like packets to send, you always send the packets that are enqueued in the high priority queues before the packets that are sent, that are stored, in lower priority queues. So here in my system, I will first send packet 1, 2, 1, then I will go to 3, and then 4, 4, and 5. So I always send the packets whenever it is available in the highest priority queue. So that's strict priority queuing, nothing fancy really. This is just default vanilla strict priority queuing. So far there is no fanciness, no P4 magic there at all. The P4 magic comes into the index that we associate to each queue. And that's where actually the P4 programmability will be very important. So we kind of like augment normal strict priority queues with a simple index, 1 per queue. And that index kind of like indicates the switch, what ranks should go into each queue. And so, these indices, we can change also at runtime. We can adapt this automatically, if you wish. And the logic is actually not too hard. So what happens is that we map packets to a queue by scanning the queues from the bottom upwards. And we kind of like put the packets in the first queue in which the condition that the rank of the packet is higher or equal to the index of the queue. And you can see this here, for instance. So packet 4 will be enqueued in the lowest priority queue because the index is 4 and the rank is 4, so it meets the condition, so the packet goes there. Same thing for 5. A packet of rank 3 will not be enqueued in that queue but it will be included in the queue just above it. And so that's the idea, is that by modifying this index, we can kind of like tweak and change how packets are mapped to queues automatically. So one thing here that I want to say is that if you give me a device with, let's say, an infinite amount of queues, then I can actually I can implement the PIFO queue perfectly using that system. And the solution here is pretty basic. The only thing you need to do is to just map each rank to a dedicated queue. So I will have, for instance, if I have only 4 ranks, we'll have rank 1 that goes to the highest priority queue, rank 2 that goes to the second highest, etc., etc. And that will always give me a PIFO compliant output on the output link. Of course, what's the issue? Well, is that in practice, you tend to have many more ranks than you have queues. So if you have like 32 queues and you have like 60 ranks, well, there is a problem there, of course. And that's, of course, why it makes what makes it challenging is that we need to kind of like figure out a way to map many more ranks into a fewer set of queues. And you can see here an example where you have 5 ranks over there and 3 queues over here. And what it means when this happens is that you will have more than one rank into at least one queue. So that's kind of like the pigeonhole principle as well. So here, for instance, you can see that rank 4 and 5 are in the same queue, and also rank 1 and 2, they are in the same queue as well. And this is where the SP-PIFO approximation will kind of like be visible. Because whenever you have this, then you can have scheduling errors. And you can have scheduling errors depending on the order in which you have put this different rank packet into the queue. Let me actually illustrate this with an example right away. So you can see here that in the top queue, the top queue contains packets 1 to 1. So here, when I will empty the queue, that will be the order over there. And you can see that we are not PIFO compliant because we have a packet of rank 2, which is scheduled before another packet of rank 1. So if I were to give you a PIFO queue instead, you would have had 1, 1, 2, 3, 4, 5 as an output. But this is just because we had to map this 1 and 2 into the same queue, and then we had the packet of rank 2 coming in before another packet of rank 1. There was nothing we could actually do there. One thing we can do, and that's where, of course, the kind of like most of the paper actually went into, is kind of like trying to figure out how to adapt this kind of like indices in order to minimize the output scheduling errors that we observe. So let me again illustrate this with an example so that it's hopefully clear. So we again take like a simple sequence over there, and then now the question is, what should be the indices in order for me to get a PIFO compliant sequence? What we already know is that this sequence that I considered initially, 1, 3, 4, this is not a good one because it will map the packet like this, and then my output sequence will have a scheduling error, 1 to 1. But what about we change this indices into 1, 2, 3 instead? Now, if you do the quick math there into mapping these packets into these different queues with these indices, you will see that you will actually end up with an allocation like this, with only the ones in the highest priority queue, then the 2 in the middle, and then 3, 4, 5 in the last one. And now, of course, in this example, you have like a perfectly PIFO compliant output. So just to show you that depending on the input traffic and depending on these indices, you can have more or less scheduling errors at the output. So here, that's where kind of like the science and the research went into. It's kind of like how can we adapt these indices dynamically in order to minimize the scheduling errors. I will briefly explain you this. Now I think I will, as I said, I will run out of time, so I will be very quick on the implementation and the evaluation. But essentially, I can already give you the cliff note. It runs in the Tofino switch. It runs actually pretty well. And the evaluation is that it approximates PIFO behavior also very, very closely. So it kind of like gives you a very close approximation. So the error is kind of like small. Let me just give you very quickly an idea though of the adaptation strategy. So what we did in our paper is actually we phrased this problem as an optimization problem. And the optimization problem is actually pretty intuitive. So what we are looking at finding an optimal mapping policy. So by mapping policy, I mean these indices, right, the vector of this index. And we are trying to find the best vector, the best set of indices that are minimizing the number of scheduling mistakes we make. In the paper, we define this notion of un-PIFO-ness. So un-PIFO-ness kind of like gives us, for a given traffic distribution, kind of like the number of scheduling mistakes we'll have for each rank. And so essentially, we have like an optimization problem where we try to minimize the error that we make. And of course, there are many different ways of solving these kind of like problems. Like one of them is using gradient descent approaches, for instance. We do that in the paper, we explain everything about it. But the problem here is that it's actually intractable to solve in practice. So I can spare you the details here. But the issue is that these optimization problems assumes that we know the rank distribution beforehand. So we know exactly how many packets of rank 1, 2, 3 will arrive, which is of course something that is not practical. So we cannot really solve this problem unless we assume that forever we will know exactly the exact shape of the network traffic, which of course is completely non-realistic. So it's a very common story, right? You have like an optimization problem which is not solvable in the purest sense. So what you do, you try to also approximate that optimization problem. And so instead of like assuming we know the entire distribution and we minimize accordingly, what we do is that we estimate an empirical distribution and then we optimize according to that. And we go even further by reducing the entire distribution to a single packet. And I will show you this in a second. But essentially, we are looking at a smaller online optimization problem now, in which we are trying to update this index only according to the previous packet that came in. So let me actually give you an intuition here. And there are two phases in how we adapt these indices in SP-PIFO. The first phase is the push-up phase, as we call it. So we start with all our queues with an index of 0 everywhere, and then the packets will start flowing into our system. So what we do is that we start to kind of like put the packets into the lowest priority queue, and then as more prioritized packets, so as lower ranked packet arrives, we start to put them into the higher priority queue. So we kind of like push up the higher prioritized packets, so lower rank, into the more prioritized queues as well. So we do that. Of course, we have like perhaps 5 queues, and if we have 10 ranks, at some point we'll run into a problem, right? Is that at some point we'll start putting packets of rank, let's say 6, 5, 7 into the first queue. And this is where we'll start to have scheduling errors. So we'll kind of like, by doing this process of like pushing up the packets with a lower rank into the higher priority queue, we are kind of like concentrating all the scheduling errors in the top queue. When there is a scheduling error in the top queue, we kind of like do the opposite process, which is we kind of like push down all the packets to the lower priority queue again. So you can really think of these two processes as what defines SP-PIFO. We kind of like pushes up packets of higher priority into higher priority queues, and then there is another process that pushes them down. And these two things kind of like go along and kind of like oscillate between them. Let me again like illustrate this with a simple example that I think will make things clear. So here we are starting with a SP-PIFO system of only 2 queues, indices of 0. And then we have an input sequence 1, 2, 3, 4. So we scan, we take the first packet, and then we scan the bottom queue first, index of 0, 4 is greater than 0, great. We put the packet there, and then we update the index of the queue as a push-up phase to 4. Now the next packet arrives, it's a rank 3, so 3 is more prioritized than 4, the rank is lower. We'll scan the queues, 3 is less than 4, so it cannot go into the first queue, so it will go in the second queue, the highest priority queue. And we'll queue it there, and then we'll update the index accordingly. So now we end up with an SP-PIFO system like this. We have 2 queues, index 3, index 4. So now we have a packet of rank 2 that arrives. You can see now we'll have a problem actually, because we cannot put the packet there. Technically, we cannot put the packet there as well, because the rank 2 is smaller than the index of 3. But since there is no other queue of higher priority, we are forced to do that there. So here we know that we have a scheduling error, and we can compute the cost of that scheduling error in the switch directly. Here it's a cost of 1. We know that we will actually have scheduling mistakes in which we will schedule a packet of rank 2 after a packet of rank 3, where it should have been the opposite. And this is where the push down will take place. So we have a cost of 1. So in SP-PIFO, what we do is that then we'll lower all the indexes by the amount of the cost. So here by the amount 1. So here we start from 3, we'll go to 2, and then 4 will go to 3. So that in a sense will kind of like push, if you want, higher ranked packets or less prioritized packet to the lower queue by doing this. And so the bigger the error, the more push down we do, so that we actually free up space for the more prioritized packet in the first queue. So that kind of like how SP-PIFO works, with kind of like these two processes, adaptation processes that are kind of like playing against each other, pushing up, pushing down, and then continuing as such. So the implementation, I will be brief here because I really think I'm running out of time, but essentially you can implement this in P4. It's actually not that hard to implement if you think about it, and you can also implement it in Tofino, on the Tofino target. And what you need to do is to maintain this queue index, 1 per queue, and that you can just spread them around in different stages. And then you kind of like, as the packet kind of like flows across your ingress pipeline, you're kind of like remembering what is the queue that that packet should go according to this different index, and that you can store in the metadata. Accordingly, if there is also a scheduling error, you need to store the cost. So you can see in the metadata, we store 2 things, to which queue that packet should go, and also if there is a scheduling error, what is the cost. And then when there is a cost, we need to do a push down, and since for those of you who have already played with actual hardware target, you know that it's hard to update registers once you have like read them. So in order to do that, we kind of like recirculate the packets, resubmit the packets actually to the input, so that then we update all the indices with our rescheduled packets. All right, so again, so that's how there are way more details in the paper, and of course I'm happy to discuss also offline if you want about the implementation. So in terms of evaluation, I will be again quick here, but the idea is that it actually works very well, as I said. So we kind of like showed with our SP-PIFO implementation that we can approximate very well scheduling algorithms, multiple kind of scheduling algorithms. So we showed how to minimize flow completion time and for max mean fairness. And skipping tons of details here, but what you can tell from this graph is that if you look at the PIFO curve, which is in reddish, and the SP-PIFO curve, which is in yellowish, you can see that they are basically almost equivalent to each other. So it actually works very well for pFabric, minimizing flow completion time, but also for fair queuing algorithms. You can see the same thing here. SP-PIFO and PIFO are very close to each other. All right, so to summarize SP-PIFO, it approximates PIFO queues. Once you have PIFO queues, you can implement any kind of scheduling algorithms, and it does run in hardware and actually runs pretty well. So to kind of like finish, and I will only need 1 more minute or 2 more minutes, let's say, looking forward about where we can go from here. Well, I think if we were to look at this picture again, where I have the control plane written in software, typically C or C++, and then the dial plane running in hardware typically, and now more and more like written in P4. So as I've shown you, for instance, the routing task, today you do it over there, and that's definitely not great. What I've explained to you in this talk is that you can do here, you can do almost all the routing tasks in the hardware. As I told you, I think this is actually likely an overkill to do that there. So I think really the answer is somewhere in between. I think routing should be not completely done in software, not completely done in hardware, but somewhere in the middle. And I think, interestingly, what would be nice is that you can actually adapt how much hardware acceleration, how much hardware offloading you have for your routing task, depending on an objective or depending on the network conditions. So how do we, let's say, have a hardware-software co-design that can be adapted dynamically? I think it's a very interesting problem that clearly we haven't solved. Another thing I think that I hope some people in the audience should solve is the interaction between the control plane and the dial plane. I think right now it's way too simple. The control plane just writes forwarding state, and then that's basically it. So I think there are like way more integration here that we should actually strive to. Like for instance, having, I don't know, like performance-based routing decisions. So like inform the routing decisions according to dial plane statistics. I think is a nice, interesting question that clearly some people are already looking at this. If we look at flexible scheduling, I think something that we haven't talked at all is what kind of cool application now can you do on top of programmable scheduler. So it's not only that you can implement algorithm 1, 2, 3 up to n, but you can also morph them. You can have 1 that turns into 2, that turns into 3, dynamically according to the network conditions. So you can probably implement something very nice here, in which, for instance, you are using different algorithms depending on the network conditions to, let's say, for instance, improve QE. And then something else I didn't speak about, but would be a nice research project. Also, how do we adapt my mapping policy, right? I mentioned this push up and push down. That's kind of like basic. I think there are like more fancy adaptation strategy here that can be thought of. That, for instance, are traffic aware. So here also, I think there is a lot of research following there. All right, I hope I wasn't too long. It's hard for me to figure out exactly how much I lasted. But essentially in this talk, I explained fast routing, flexible scheduling, and then some ideas of how we can move things forward there. Here, I would like just to finish by kind of like mentioning my research group. So really they did all the work. I'm kind of like just the messenger here. And also, of course, as I told you, there are so much more details into the papers. So we have a hotnets paper here, an SDI paper, and two NSDI papers about Blink and SP-PIFO that you can look into for more details. With this, I'm actually happy to take questions if you have any. Also, I will be online. You can ping me on Slack, or I will try to join this kind of like hub rooms. Not guarantee I will manage, but by all means, I'm available also during the day if you want to chat more. And then I will just finish by saying that please take care, stay safe, stay healthy, and happy to take your questions. Thanks.